Okay, so ladies and gentlemen, we've already come to the final talk of today. It has the very promising title 50 Ways to Leak Your Data, an exploration of apps circumvention of the Android permission system, and is held by Serge Egelman. Serge is the research director of the Usable Security and Privacy Group at the International Cybersecurity Institute, ICSI, which is an independent research institute affiliated with the University of California, Berkeley. He also holds an appointment in the Department of Electrical Engineering and Computer Sciences, and he is the CTO and co-founder of App Census, a company performing on-demand privacy analysis of mobile applications, which they call privacy analysis as a service. Serge is going to talk about how Android application circumvents the system's permission model in order to gain access to protected data without the user's consent, which is something that shouldn't happen at all, obviously. So welcome, Serge. We're pleased to have you here, and we are ready for your talk.
Thanks for having me. Let me open this up to the screen sharing. Okay, can everyone see my screen?
Yes, we can see your screen. We hear you. Everything is fine.
Great. Okay, so yeah, thanks for the introduction. I'm Serge Egelman, and this is work that my research group has been performing over several years and with a bunch of others at other institutes. So we've been looking generally at the Android permission system for a couple years now in terms of what users understand about what they're granting to apps, and basically looking at from the user perspective in terms of how can we design better controls for end users. And so everyone's probably familiar with the existing permissions dialogues. So now there's this the runtime permissions on both Android and iOS. Originally when Android first came out, there were a list of permissions you would get at install time, and the problem with that is that it lacks context. Most people who are using an app don't really have any idea of how location data or microphone data or any of that might be used, but by having the runtime prompts, that gives some additional context, such as you were doing something such as clicking a button to find stuff near you, and therefore the app asks for the GPS location. So in that situation, there's the contextual information that makes the permission request a little bit easier to understand, especially if you're trying to determine whether or not the data access is appropriate. So, this is now pretty, widespread. It allows users to allow or deny access. And it supports this notion of notice and choice, which is sort of the governed privacy regime in most countries, where users are presented with disclosures and then can make an informed decision. So the question that we were looking at is, does this actually work in practice? So from the several years of research looking at Android security generally, my group and then another group doing research at ICSI have been looking at instrumenting various parts of the OS, as well as creating tools to help us look at traffic to try and figure out what apps are actually doing with data. So my group for several years has maintained a fork of Android where we have instrumentation so that we can monitor every time an app tries to access data that's protected by the permission system, such as accessing the location data or the call logs, any of that stuff. So there are several places throughout the OS where when data is accessed through the Android API, that triggers a permission check, and then the OS checks to see whether the app has been granted that permission before deciding whether or not to share the data through the API. And so that's our goal is to monitor when those APIs are actually called. In parallel, there was this other project going on at ICSI called Lumen, which is a user space traffic monitor that does TLS interception via the VPN interface. And so by combining these two tools, our instrumented build of Android and a network monitor that allows us to do deep packet inspection, we can start looking at, what data goes to which parties, answer specific questions about specific data types, such as, which parties, share location data, what types of persistent identifiers are collected, are they shared across apps, stuff like that. And so in using these tools, we basically had to build a workflow to build data sets. And so the first step obviously is downloading lots of Android apps. We have a scraper that we've been using from the Play Store, as well as various other sources of Android APKs. Obviously step 2 is then running those apps to see what data they access using the system instrumentation, and then where it goes using the network instrumentation. And then we can see exactly what personal data was accessed and where it was sent. And so the first problem, obviously, is the apps need to actually be run so that we can see what code gets executed and what that code actually does. Generally, this is thought of as a human task. And so to start out, we hired a couple students to play a bunch of games so that we can examine basically just the code coverage for normal use of apps. People playing, what sort of code coverage can we get? And then we compared that with the Exerciser Monkey. So the Exerciser Monkey is a tool that basically it's for fuzzing the UIs of Android apps. It generates random clicks, swipes, and so forth. And so we compared that with the undergrads, and we actually found that the Exerciser Monkey got equivalent code coverage for about 60% of the apps that we tested. And so that led to us building what is essentially a click farm. We now have about 50, 60 devices that are running apps. And this is all part of a whole pipeline. So we have, at the heart is the test bed, which is basically just phones running our custom, build of Android with all of the instrumentation. We feed it apps from an app repository that we're maintaining, and then we feed that, both simulated user actions and real user actions, which I'm going to get to in a little bit. That goes into a results database, which basically shows what data was accessed by apps and what host names received it. And then we post that online. We have a website where you can search for apps, and we've been working the past year building an API for all of this. So you can go to search.appcensus.io. This is basically our collection of free apps that we've been monitoring. It shows what various apps do. This site is actually in a state of flux because we've been working the past year on the back end. So we now have a set of tools where instead of the monkey, we now have a remote desktop feature where we can actually just play apps within the browser. And so that's what we've been doing for the startup. We have, testers in one place who just use the browser to play apps, and the phones can be located anywhere in the world. And so to, just give an example of, what we see internally, we have maps of data flows, and we flag various things such as, abuse of the permission system or exfiltration of certain other types of data that are prohibited by policies and so forth. And so right now, this is all what we see internally, and it's, we're dog fooding it, but eventually this, this part is going to be open to the public. So what have we been using this for? So one of the things is uncovering deceptive practices, and that's a large part of this talk. But there are a few other things, which I'll get to a little later. So, when we talk about security, often, we have security mechanisms that we put up, and obviously those security mechanisms are only effective insofar as users can't get around them. And, we see this both, online in terms of computer security, but also in the physical world too, right? When security barriers are put up, if there's an easy way around the security barrier, people will do so. So specifically, we want to look at side channels. So, a side channel is, where you have, say, an app that tries to access data that might be protected by a security mechanism, such as the Android permission system. The issue is if there's a way around that security mechanism, such as getting access to the same data that's stored in a different place that's not protected by the permission system, that's known as a side channel. Covert channel is a similar thing where you have an access control mechanism and you have, one app that has permission to access the protected resource, and then you have another app that doesn't. Well, if the app that doesn't have access is able to communicate with an app that does have access, then, that's another way of evading the security mechanism. So using our instrumentation, we started searching for evidence of side and covert channels that were occurring. And then the goal was to figure out, what those channels are and how they're being used exactly. And so to give an, I guess, more detailed overview of how the instrumentation works, we have this app corpus. We can then, feed the apps through the static analysis, parts to look at what data apps have permission to access. So what permissions are listed in the manifest file. But then we could also add in the dynamic analysis to look at what apps, what data those apps are actually accessing in practice with the instrumentation code, as well as then where they actually send it. So we can then compare these two sets. So for instance, we can see, which apps are allowed to, access a certain type of data, and then which apps are sending that out. And if we, subtract those to look at what apps are sending data out but didn't have access to it, then we consider those apps that cheat. And so these are all operations that we can do automatically using our test bed. What happens then, though, is when we see apps that cheat, now it becomes a matter of reverse engineering to figuring out, you have to figure out how they're doing it. And this is largely a manual task. And so let's take a look at how this works. So we have two sets here. So we have the apps that don't have the location permission, and then we have apps that are transmitting location data. So these are, pretty easy queries for us to do on our database. And, we did this about a year ago and found that there were 1,300 apps that were transmitting location data without the location permission. And so, that obviously the intersection of these two sets should be null. These should not be overlapping. But in fact, they are, and that suggests the presence of either side channels or covert channels. And so once we, uncover the existence of one through the reverse engineering, we can then do that. We can then generate a fingerprint for that particular chunk of code that was violating the permission system. And then once we have a fingerprint for the code that's the exploit, it's just a matter then of searching our entire database again for existence of that. And we might uncover situations where there was an app that was granted permission to access certain data. It transmitted that data, and so we didn't flag it as a potential side channel, but the code existed, and that's because during testing, the permission was granted. And what that means is during testing, if the permission was not granted, or if a user would use the app under different circumstances and not grant the permission, then that suggests that the app has the potential to exploit the side channel instead. So looking at a few of these, a lot of them came down to sensitive data that's protected by the Android APIs, and the permission system that's available elsewhere outside of the Android APIs and therefore not protected by the permission system. One source for a lot of this information is the proc file system. So proc is a virtual file system. It stores lots of information about the hardware of the device, the running processes, and so forth, including sometimes contents of memory. It also includes networking information, such as the ARP table. So if you open up procnet ARP, that up until the most recent version, I believe in 10 this was fixed, procnet ARP was readable, is world readable. So any app can open that, and that has the MAC address of the upstream Wi-Fi router. Now, the BSSID, or the MAC address of the upstream router, that can potentially leak location data, because those tend to be in fixed places. There are many public databases that map the MAC addresses to GPS coordinates. And so that's why, for several versions now, accessing the BSSID was governed by the location permission. But obviously that's all out the window if it's world readable on the file system. So, one of the SDKs that we found doing this looked pretty blatant. So here what's happening is this is a decompiled SDK. It calls this function is permission granted, which, as the name indicates, checks to see whether the permission was granted to the app. In this case, it's the access Wi-Fi state permission, which also governs the BSSID. And so if the permission was not granted, it then calls this, jumps to this line and calls this function called get device MAC address from ARP. And here you see it opening procnet arp, reading the value from there. And what's happening here is this is pretty explicit, right? It first checks to see whether it's it's able to get the data through the allowed way through the Android API, and then only failing that does it then exploit this side channel to get the data anyway. And this is actually pretty pervasive. So we found lots of apps that had the code to do this, and many of these apps correspond to billions of installs. So these are these are SDKs, but it shows the number of apps that they're in, and then the total number of installs for those apps. Another vulnerability that we looked at that was actually being exploited is using the universal plug and play protocol. So this is designed to help with configuring new Wi-Fi routers that are added to a home network, but it also leaks information about devices. So we found at least one app that was just directly opening up a socket to the upstream router. So this, just getting the information about the device's IP address is not something that was considered sensitive, but knowing the IP address, you can attempt, .1, try .1 on the network, or even, if you get the router, the routing table directly, and then it opens up a socket to that router. And then using the UPnP protocol, it queries the BSS ID and then shares it with lots of other servers. Another one that we found was also using the shared file system. So here's Baidu, which is in a ton of apps. So Baidu checks to see whether the app that it's in has been granted permission to access the IMEI, which is a hardware-based persistent identifier that's not easily reset. So what happens is if an app has Baidu and has been granted access to the phone state and identity permission, which governs the IMEI, it then saves that data to the file system. And we found that the Baidu apps with this permission were writing this file, and it looks like base 64. Unencoding it, we get binary data, and so at that point we started tracing through the program to figure out what's actually writing this. And here what we found was keys in code, bad practice but not surprising. And using this key, we're able to easily decrypt what was being stored. And in fact, what was being stored was the IMEI and the device ID, which I think was the hardware serial number. And so it stores this to the file system so that when an app that has Baidu in it runs and doesn't have access to the IMEI, that app will then just check this known location on the file system to see if an existing app on the device has already written this file containing the IMEI. And so we found 153 apps that had this encryption key embedded in them. Of those, half sent, almost half sent the IMEI. Now, what this means is, during dynamic testing, especially when we're using the monkey, this is largely a stochastic process of what code gets triggered. And so it's possible that if the monkey played with the apps for a longer period of time, or if real users use this, there would be more occurrences of apps sending the IMEI. And of the ones that we did observe actually sending it, 20 of those didn't have the IMEI permission. But it's not limited to Baidu. So we found derivatives of this vulnerability, or of this exploit, in Salmon Ads, which is another advertiser and tracker. Baidu I mentioned, which is in a bunch of popular apps. Another one that we found is looking at native code. So Unity is in a ton of apps. We actually found over 12,000 apps that had code to transmit the MAC address, which is something that theoretically isn't readable by apps and hasn't been since Android 6. So starting in Android 6, when apps tried to access the MAC address, they get the string of 020000 and so on. But we noticed that apps, were sending the real MAC address to Unity's servers. And it turns out that the reason here is that they were using ioctls in native C++ code, and with the native C++ code that goes around the Android APIs, and therefore there aren't any permission checks on this. And so there are places on the system where you can still find the MAC address, and in this case, the I octal is enough to return that. We actually found another one of these with the Wi-Fi MAC address being shared with apps just last week using a different exploit. We reported it to Google, and we're told that they're uninterested in fixing it. So GPS data. So we saw Shutterfly was flagged by our system as sharing GPS coordinates with their servers without holding the location permission, and this was because they were looking at EXIF metadata found in the photo library. So to access the photo library, you just need the permission that governs access to the shared file system where the photo library is saved. And so any app that has the read from the shared file system can open up the library to look at the photo metadata, which invariably will contain GPS coordinates, and invariably GPS coordinates of places what the user has been, probably sufficient to infer where they live exactly and maybe their other activities. And so all of these behaviors that are circumventing the permission system were due to the use of third-party SDKs. So the real takeaway here is in many of these cases, it's likely that the developers had no idea that, not only were their apps violating, Google's policies for, use of, certain types of user data, but they probably had no idea that any of this was occurring. But nonetheless, these app developers are still liable for it because it's code that they chose to bundle in their apps. They're releasing the apps with their name, and those apps, are violating these policies. But they might also be violating their own privacy policies if the developers aren't aware what data collection is actually, taking place. And so, looking at what the privacy behaviors are of an app is a lot more than just looking at what permissions were requested or whether SDKs were bundled. What matters is what's actually being sent. So, what we found is that the permissions really don't, play a complete picture. If an app, says that it's only declared these particular permissions, that doesn't necessarily mean that the app doesn't have access to those data types that are protected by those permissions. And so, app developers need to do a lot more to try and figure out what their app is actually collecting, when they're using third-party code. And so for, most of the ones that I've mentioned in here, we've reported those to Google and they've been fixed in Android Q, but I think there's a lot more work that needs to be done. So, there are a lot of, software updates for security issues that happen over the air. There are hot fixes that come out, but not really the same with privacy. So, as much as they say that privacy shouldn't be a luxury good, that's very much what's happening here. If these bugs are only fixed in the bleeding edge, whereas 95% of users aren't using Android Q, 95% are on 9 and below, that's a problem because most of those users aren't getting the privacy protections that they think they're getting. So with the remaining time, I was going to go over some of the other fun things that we found during the course of doing this research. So we see a lot of obfuscations that appear in code, and again, this is all stuff that we see in SDKs. So here is a transmission from Chartboost. We can see this field marked identity. Does anyone want to? I mean, so it's obviously that this is just base 64, and what's being copied is the advertising ID alongside the device serial number, which is a violation of the ad ID policy that Google has for the platform. Here's another one. Does anyone want to guess what this is? It's hard to see any hands from this view, but you can see here that this looks like base 64, but it's not really. But the indication is if you try and decode this as base 64, it doesn't decode properly. And the key that we figured out was looking at the last two characters, the YE. For those of you who have looked at a lot of base 64, you'll know that when JSON objects are transmitted, they usually begin with EY, which is a opening curly bracket to denote a JSON object. And so this is what we refer to as the 46 ESAB encoding. Basically, they took they take all the data, they save it as a JSON object, and then they take the base 64 and flip it around so that it can't be easily decoded until you flip it around again. And once we know to do that from just looking at the underlying data, we can see that again, it's transmitting stuff that it's not supposed to. Other weird stuff that we see, this I have no idea. This maybe this is just bad coding. Maybe I'm thinking too much about it. But here they send the IMEI, then they send the MD5 of the IMEI, then the SHA-1 of the IMEI, then the SHA-256 of the IMEI, and same thing again with the Android ID. And what's interesting is, what's interesting here is that not only do they, the reason why they're sending this twice as the MD5 and the SHA-1 is the function that sends this, it calculates the MD5 of the hex characters, both as uppercase and lowercase. In the case of the IMEI, it's all numeric, so you get the same hashes. With the Android ID, that's not the case. There will be a difference, with uppercase versus lowercase, and so they collect them all. Why they do that when they're also collecting the unencoded data and could be hashing it backend to on the backend to figure out if they're matching it elsewhere from hashes? I have no idea. Another thing is, keys and source that I mentioned. We see this a lot of the time. So yeah, I guess there's not really much more to say about that. Bad keys and source. This was a fun one. So in the traffic, we saw a key name as locations. And we saw this string, which looks like base 64, but when you decode it, you don't get binary. These are all ASCII characters, which was an indication. And what we discovered, what was happening was that it was just XORing. And so what it's doing is it takes location coordinates and XORs them with encryption key, encryption key, encryption key, and then XORs them with start app, start app, start app in LeetSpeak, where start app is the name of this SDK. There's incompetent sharing of PII is another thing that we've seen a lot of. So one thing when we first started this project, this was about 2 years ago, one of the things that came up was as a sanity check, I just did a search. I was looking for apps sharing lots of location data, and we found that CVS, which is a big pharmacy chain in the US, they have an app, and according to our instrumentation, it was sharing location data with 40 different third parties. My first thought when seeing this was, surely there's some bug with our instrumentation that, all of these companies couldn't possibly be collecting, user location data when using this app. But, in fact, it was correct. And it turned out what was happening was whatever, genius coded this app decided to add location coordinates to the user agent string. And because the app basically consisted of a whole series of web views, every time third-party content was loaded in one of these web views, it received the location data as part of the user agent string. And this was obviously a bug in the app. It shouldn't have been designed this way. And so I spent about an hour on their website trying to find a technical contact to email about this. And after an hour, I finally gave up and just sent an email to customer support pointing out the problem. And of course, I got this very nice, form email back saying we don't share data with anyone, which obviously was untrue. And so at this point, there wasn't, since I had exhausted all of the ways I could think of trying to alert CBS to the issue, I tipped off a journalist. And then when it became actually a news story, they then fixed the error. And so, this also, illustrates the importance of having, technical contact information available on your website. So I'll leave it at here and open it up for questions.
Okay, thank you very much, Serge. So I not only learned your name is pronounced Egelman, not Egelman, sorry for that, but I also,
that's fine.
but I also came to know that 46 ESAP is a thing apparently. This was quite funny. So we're up for the final Q&A session of today. So please don't hesitate to ask whatever you like to know. We already have 2 questions in the chat. The first one is from Renee, who asks, have you seen those SDKs you talked about adapt their behavior now that newer Android versions block access to ProcNet, to the ProcNet directory and other such channels that were previously possible?
That's a very good question. We're certainly monitoring for that. I don't think we've collected enough data to really see if that's been impactful, because the fundamental issue is for 95% of Android users, that vulnerability still exists and it's still being exploited by lots of apps. And that's because the fix for it is in, I think it started in 10. And so, with that fix, only 5% of users have upgraded, because most Android users aren't buying a new phone every year so that they can get access to the most recent over-the-air updates. And so I think that's a big issue, is that the exploits that have been discovered and the vulnerabilities patched are still being exploited, right? Because it only goes to the bleeding edge. So it's a good question. It's something that we're looking for, but we're not really, seeing much of it yet, because there's so many other ways of collecting the same data.
Okay, thanks. Another question from Renee. Do you think that scoped storage will mitigate those side channels between apps in a sufficient manner? Or put differently, which other way would you, in the role of a malicious app developer, go on an Android version with scoped storage?
Yeah, no, that's a really good question. I mean, the short answer is yes. I think that scope storage really solves this problem a lot. I think the big problem was that with shared storage, one, that gives apps a lot of power if they can read the entire shared file system, and if the shared file system is sort of the go-to place for apps to store stuff. So if apps are storing lots of sensitive data there, even if they're a perfectly benign app that isn't intending to exploit any of these things, by putting data on the shared file system, then they're a target for other apps that might have less benign intentions. And so the best thing, I think, is just having the scoped storage. I suspect that will solve a lot of it, but increasingly, again, we found some new findings last week that seem to all be due to native code. And I don't really have a good solution around that, other than moving a lot of these protections into the kernel. It seems, I haven't looked at the code directly, but like the proc file system fix, based on just playing around with that fix, I assume the way it was implemented is by looking at the kernel, looking at the UID of who's trying to read from the proc file system, because when it's an app, it shows the file the file doesn't exist. Whereas if I using ADB, I can still see it. So I think there's a lot more that you could do with the kernel to look at what user IDs are reading from what files. So yeah.
Okay, thanks. Yeah, let's hope that scope storage will make things better in that regard. So we have a question from Daniel Thomas, who asks, is the problem with the privacy breach fixes that fixing them changes the potentially unofficial API and so requires a new API version? Is that a problem?
It's a problem, but I mean, isn't that I mean, that's the problem of using unofficial APIs to do things, right? I mean, if you're relying on exploiting a vulnerability to get the data that your app needs to function, that doesn't seem like a great long-term solution. Instead, maybe you need to then focus on only using supported APIs so that you don't find yourself in that situation.
I meant that the reason why they might not be backporting it is that they might be worried about it being a breaking change. I'm not suggesting that would mean that they shouldn't still do it, but I'm guessing that's the pushback from the backporting thing.
Sure, but it's, I mean, so that's, the calculation is, should we, if we fix this, developers are going to complain that their legacy code that was that wasn't using supported APIs is breaking. that's one side of the coin. The other side of the coin is, users actually get to control what data is accessed by their apps. And so, given those, those two trade-offs, it seems like, making it so that the permission system actually does what it says it does, and the controls actually, prevent the data from being accessed so that users can actually have a better understanding of what data is being accessed. It seems like that should be the priority, but it's not. So
I'm thinking that there was a remote code execution vulnerability that required a API change, and you had to wait for it didn't get backported. You had to wait for the upgrade, and you still had the remote code execution until you changed your phone.
right.
And so that fear of changing the API isn't just a privacy thing. Like, you can still have remote code execution that can live for ages because they're just afraid of breaking people's apps. They might have different policy now, but that was the case.
No, sure. I mean, like, there's no doubt that some apps would break, but those apps are breaking. The reason why those apps would break is because they were using unsupported APIs for their functionality. And so, I mean, if the risk that developers took is coming back to them, that's kind of their fault. And instead, instead choosing to provide users with controls that don't actually work, that doesn't seem like it's an acceptable trade-off.
Yeah.
Okay, thank you very much. I do have a question. So you told us you compared the code coverage of UIMonkey with the actions of your students, and it was quite similar for 60% of the apps. So I asked myself, how much more code coverage did your undergrads get for the remaining 40% of the apps approximately? Much more, or is it neglectable?
I don't remember. I mean, so this was a specific type of app. That statistic was when we were looking at games. That's how this initially started. So one thing I didn't talk about in this talk was, one of the first uses for this infrastructure was testing kids apps, because that's actually one of the few areas in the US where there actually is, privacy law. And so we wanted to see whether apps that were marketed to children were obeying the children's privacy law in the US. And so for children's apps, we got pretty good coverage because those apps are a lot simpler. The reason why we've shifted to doing this, the remote desktop solution, we're also doing some work that we haven't published yet to try and improve the Monkey. But by and large, for any sort of complicated app, the Monkey isn't a great solution. That said, it captures a lot of the stuff that we're interested in because, again, most of the stuff that we're finding is due to third-party SDKs that have been bundled with the app. And in many cases, those SDKs start transmitting, all of the personal data that they're going to transfer as soon as you run the app. So not in response to any particular user input. Obviously that changes when it starts serving ads. The user clicks on those ads, and there's a whole, attribution chain, and lots of other third parties get contacted. But by and large, most of the SDKs that are bundled communicate personal information to their servers, at time zero. And so that's why the Monkey, for many purposes, is actually sufficient. But yeah, but the Monkey is very stupid, and so
it is.
Yes.
Okay, thanks. Another question, do you think ioctls or let's say native C++ calls in general may be used for even more questionable techniques like what you show us for getting the MAC address? I think it was the MAC address.
Yeah. So we found two just last week. One was gathering the BSS ID, another was gathering MAC addresses. Those weren't ioctls, but they were other Java APIs that were, being used outside of the permission system. So the data was available in some, other Java APIs that weren't protected. Yeah.
Okay.
But yeah, I mean, there's a lot of this out there, right? So we find stuff, new stuff like this all the time.
Yeah, if you do, I hope you tell us next year if there is another symposium next year. Okay, I guess that's it regarding questions, if I'm not mistaken. So thank you very much again.